All right, so today we're going to start the final topic for this class. It is buckling or instability. And in order to introduce that, I want to talk a little bit about the World Trade Center collapse. I am not going to be addressing, nor am I qualified to address, sort of the human tragedy that occurred that day. But I will address the technical aspects, and in particular, I want to address these three questions. Why did the towers collapse? Why did they stand for so long after the impact? And why did Tower 2 collapse first, even though it was impacted second? So, and in order to do that, I'm going to use these two sources. I think they're still largely considered the sort of seminal reports on this. The first is the Silverstein report. So these were owned by Silverstein or managed by Silverstein Properties. They were actually part of the Port Authority of New York and New Jersey. And the NIST report. So NIST is the National Institute for Standards and Technology. And it's in the U.S. Department of Commerce, and they took the lead from the government standpoint to investigate and ultimately answer these three sort of key questions. So before we jump into what happened, when they were impacted and then shortly thereafter, we've got to talk a little bit about what the World Trade Centers actually looked like, right? So this is the design concept, and what you see here is, so this guy, let me just write here, this is known as a tube-in-tube construction. So Les Robertson was the lead structural engineer, and these buildings, in fact, were quite innovative for their time. They were built in the 70s, and they had a centralized core, right? So a central core here, right, where all of the elevators were located, right? And then around the outside, they had a series of very closely spaced columns, right? So that is the sort of tube-in-tube construction, right? So there was an inner tube, right, that housed the elevators and all of the mechanical systems, right? And this is known as the core, right? So that's what they may refer to as the concrete core. There's a number of, basically a rectangular core that was composed of shear walls. And then on the outside, they had these closely spaced columns. And in fact, when you looked at the World Trade Center, that's what you saw. You saw these very closely spaced columns. I think they had them clad in some sort of aluminum or stainless steel or something that did not sort of corrode or somehow discolor with time. But behind that cladding was just large steel eye sections. And you can go back and look at YouTube and understand, there are some videos of how they had built these. And basically what they did is take these column sections, I think they were like maybe 3 or 4 columns wide, so that was like maybe 10, 12 feet, 14 feet, and they were about 3 stories tall, and they would just sort of pick them up and pop them into place on top of the set of columns that were below, weld them up into the in the field, and then continue to move, grab another set of columns and put that into place. And that's effectively how they built the outside tube of the World Trade Center. So it was very efficient, in fact. And one of the keys to the success of the World Trade Center was really the the location of the elevators in the central core. And in order to allow that to happen, and for it to be sort of efficient for a 110-story building, they had to have express elevators as well as local elevators, right? And if you look at the local elevators here, you can see they were stacked right on top of the local elevators that were below them, right? So those are local elevators. These are in the same tubes, right? But they only went for 1/3 of the structure, right? And then you had these express elevators, right? So if you worked on the top floor, right, you would take an express elevator up to, say, floor, 70, and then from 70 up, you would take these local elevators, right? And so that was actually one of the really big innovations that that allowed this building to be so successful. I guess the other thing I want to mention before I get into one of the unique parts of the design that made the building attractive to work in, but ultimately created this vulnerability that, of course, nobody understood at the time. But these were really massive buildings, right? So if you look here, 208 feet by 208 feet, they were square in plan, right? That's almost a full acre, right, of office space. Well, I shouldn't say office space because some of that is the core. But if you notice the yellow here, that is all open space, right? There are no columns there, right? Or there were no columns there. So if you've ever had the chance to get into something like the Empire State Building, and I suggest you do if you have the chance, what you'll notice is that it's sort of a forest of columns, right? The only way they could put that building up at the time that they did, and I think it was the 20s, was by just relatively closely spaced columns. And the sense that you get when you're in that building is sort of claustrophobic because there's just so much sort of structure around you. Well, if you were in the World Trade Center, it was like wide open spaces, right? And effectively what you had was this interior concrete core, and then you had these trusses, right, that spanned out to the exterior columns like that, right? And so they could span, the 50 feet or 75 feet that was, and cover that open space and leave these, wide open areas for people to work in. And so if you were working in the World Trade Center, you didn't think at all about sort of claustrophobia, right? Because it was wide open spaces. And if you see some of the videos from that day, or maybe other days as well, you'll notice even in the first floor that everything was just massive wide open spaces, right? And the way they were able to do that again was by focusing the vertical forces within this concrete core and then outside along the perimeter, right? And that was those were the very closely spaced columns around the outside there. Okay, so that is the overall design. So let me shift gears and talk a little bit about sort of what happened that day. So these are the impacts. I'm going to draw two towers here. So this guy, I guess we'll do it like this. So that's the inside core, and those are the outside, closely spaced columns. Then I'm going to draw a vertical view of this like that. And I'm going to do that again over here. Okay, and then again I will do vertical view. So this one is Tower 1. Also known as the North Tower, I believe. And this guy here is Tower 2, also known as the South Tower. So what happened is the North Tower gets impacted first, and it gets impacted in the middle here. And so this is sort of the damage pattern, and I'm not gonna, it's certainly not exact, right? But that's roughly where the impact occurred, right? And it occurred between, so sort of laterally here or vertically here, it occurred between the 93rd and 99th floors, right? So it was relatively close to the top, right? And it was, importantly, directly in the middle of a face, okay? Then if we look at Tower 2, right, Tower 2 actually gets hit from the southwest, right? They're sort of heading southeast corner, with the plane heading to the northwest. And it gets hit like right here. Right? And it gets hit somewhere much lower. So it got hit in this region here, which was floors 75 through 85. Right? So just looking at the where those impacts occurred, both in plan view and then also in elevation view along the side of the tower, we see a few things, right? One, we see, and I guess I'll do these in green, right? One, we see that the impact, let me clean that up a little bit. That the impact occurred at a corner, right? And so just like with a stool, right, if I pull out one of the 4 stool legs, that stool is sort of getting pretty unstable, right? You can sort of rock over. There's really little to stop any sort of rotation of the stool towards the stool leg that was removed, right? So that's the first thing, right? So this is less stable. Right? And then the second is that it got hit lower, right? So there was more weight above the impact. Right. So not only did this tower get hit in an area spatially, like in the plan view, that created a lack of stability because we were effectively removing a corner, right? It also got hit lower on the building as well, right? And as it got hit lower on the building, there was more weight above it, right? So not only was I knocking out, in this case, in fact, more columns, but also in a more vulnerable part of the tower, but the remaining columns actually had to carry more weight than Tower 1, right? And you can see where Tower 1 was hit. Just visually, you could see it's much more stable situation, right? I retained basically the four corners, right, of the stool, which was not the case for Tower 2. Right? That's the first thing that I wanted to talk about, and this is what I think is sort of generally understood about, you know, why these towers collapsed. But there's sort of two other reasons that, I think there's four reasons total that sort of answer all of the questions that we had posed previously. And these other reasons here are a little bit more challenging for, let me say, the general public to understand, right? So I'm going to do my best to try to explain these. So let me over here draw the core, right? So this here, I'm going to label it as the core of the building, okay? And then we have, you know, every floor we have these trusses that span out, right, to the exterior columns, right? So this guy here, that is an exterior column, right? And these are what we'll call floor trusses. Right? And those floor trusses are really important. That's how we can get these really, you know, sort of open spaces here. Right? So when the plane, in both cases, in fact, when the planes impacted, right, they did a few things, right? So let me do this. In fact, let me do this in sort of pink. So the first thing that they did was that they damaged a series of these exterior columns and floor trusses, right? So these guys are being removed, right? And that does a few things, right? One, it increases the unbraced length, right? So if this guy here, I'll do it, I guess, in red. So this is, I guess we call this 3. And I'm going to write it sideways, so. So we've increased the unbraced length of the column, right? So I've removed those lateral supports, and the columns that were not cut, right, but were just adjacent to this, they now have a longer unbraced length, right? So if you think about, you know, like when you're out at a diner and you have a drinking straw, if you you know, push on either end of the drinking straw, that straw is going to kick out to the side. That's what we know as buckling, right? One of the things we're going to derive very shortly here is the relationship between the unbraced length, right, and the buckling load. And it turns out that if you double the unbraced length, then you reduce the buckling capacity by a factor of 4. Right? So it's not just linearly related to that. Right? It's a lot more than just linearly related, and it's exponentially related. So So what we did here is basically increase the unbraced length from in between the floors. The floors are there, they're bracing these columns, right? But as I remove those floor systems, instead of spanning, let's say, 18 feet in between floors, now all of a sudden my column is spanning, say, 36 feet, or in some cases maybe even longer, right, than that. So that was a major reduction in capacity. And then finally we had, I'll do this I guess in green, finally we had a fire in here, right? And that fire did a few things. Well, first the impact blew off the fire protection on these trusses, right? And so as the fire burned, the trusses began to soften. And in fact, the trusses began to bow like this, right? And the one below would bow as well, just like that, right? And what happened with those trusses is, and you can sort of see this, if you have a rope, right, and you're trying to pull it taut and then support something vertically on the rope, right? As that rope begins to sag, what happens, you can feel it's sort of pulling in on both sides. And that's what's happening here. These trusses are beginning to pull in on these columns, right? And so these columns begin to start bowing inwards, right? And that's actually what this picture is here on the right, right? So what you can see, this is the collapse sequence right before, what is this? The south tower. So this is right before tower 2 collapses, right? You can see the columns are starting to bow in, right? They're being pulled inward with the because of the sagging of the floor trusses, right? And then right here, you can look, this is the image taken directly before the collapse initiated, right? Maybe it has in fact already initiated, but now you can see it's not a subtle bow anymore, right? Those columns are actually being pulled directly in, right? And if you look, you can see some videos of this. They've slowed it down, right? If you're going to go on the internet, and I suggest you do, there's a lot of really good information there. There's also a lot of bad information there, right? So again, be careful about the sources that you look into. But generally, the NIST report, the Silverstein report, they're pretty well respected as sort of trying to take a kind of an honest look at what happened here, and there were certainly a lot of structural engineering talent, on both of those teams, and so that was the fourth sort of issue here, right? Is that the columns were being bowed in. And so this could be called a P delta effect, right? Where as these columns get bowed in, right, and I'm going to try to do this here, and I apologize, I know it's sort of a small, let me do it this way. Right, so I put my load there, right? If if my column is deformed, right, so it looks like that, right? Now that delta results in a moment, right? If I take the moments about midspan here, because my column is bent, and in fact, let me try to accentuate this a little bit so I don't confuse anybody. Right, so because my column is bowed like that, that delta times the P, right, which is the vertical force here, right, that creates a moment, right? And that moment is going to act to increase the delta, right? This is basically how buckling occurs, right? Something begins to cause an out of straightness, right? And that out of straightness begins to deform the structure, right? Because it creates what we might call, some people call secondary moments, right? And those are moments that result from the deformation of a column. Sort of as it begins to kick out to the right, I generate a moment. That moment kicks it further out to the right, which increases the amount of moment that I have, and I'm left with a very unstable situation, right? So this, in effect, these four reasons here are exactly why, and let me just go back here, exactly why the World Trade Centers collapsed, right? So the columns that, you know, for their first, whatever it was, 30 years, were more than sufficient to maintain equilibrium and stability, right? They were compromised because not only did I increase their unbraced length, which drastically reduces their capacity, but I've also been heating them, which is reducing their elastic modulus, right? That's sort of a fifth reason. And the reason they stood for so long, which thank God they did because so many people got out of those towers, I think, you know, except for a few, almost everybody that died below where the planes hit were firefighters, you know, first responders that were going in to try to help people get out. But pretty much everybody else had gotten out of those buildings except for obviously the folks that were above where the planes hit. The reason that they stood for so long is because the heating of the fire and the sagging of the floor systems played a really important role, right? And so it took some time for that to heat up. And the reason Tower 2 collapsed first, even though that it was hit second, was because it was hit in an area that inherently compromised its stability, right? And it was also hit lower, and so there was a lot more weight, a lot more potential energy, if you will, that was above where the damage was, and so it was much harder for that tower. I should say this: that the tower lost equilibrium and became unstable much quicker than Tower 1 did. All right, so that is our introduction. Next time, we are going to actually go through and sort of explain a little bit more about what buckling is, how it occurs, and then we'll do the derivation.